What if I told you there's, well, a new way to find exact solutions to mathematical challenges we previously thought were pretty much beyond our reach? Today on the deep dive, we're plunging right into that. Our mission to understand how we find the precise, exact answers to really massive, high degree polynomial equations. The kind that have traditionally left mathematicians scratching their heads, often just settling for good enough approximations.
That's absolutely right. I mean, for a polynomial of the scale we're talking about today, let's say degree 19, your traditional numerical methods, think Newton's method,
Right.
they only give approximations. And the fundamental limitation there, well, these approximations are always susceptible to rounding errors. Crucially, they just cannot guarantee an exact value. You're always left with a close enough, which, in many science or engineering fields just isn't sufficient.
Okay, and that's where this truly groundbreaking work comes in. Today, we're going to unpack Ezouidi's theorem. This isn't just like a small step forward, it's described as a revolutionary method. It completely redefines how these complex problems can be solved. It promises exact symbolic solutions where other methods just give you estimates.
Right. And what's fascinating here is the contrast with some really established mathematical principles. You take Abel's theorem, for instance. It famously states that certain polynomials cannot be solved using radicals, solutions expressed just with basic arithmetic and roots like square roots, cube roots. Ezouidi's method is so profound because it shows that even polynomials which do have radical roots can in fact be solved exactly. It effectively bypasses those long-standing limitations of classical algebra and the numerical methods we mentioned. It's a real conceptual leap.
So, for you listening, this deep dive is basically a shortcut to getting well informed on a truly paradigm shifting mathematical approach. We're going to walk through solving a specific degree 19 polynomial, showing you how Ezouidi's theorem works its magic, step by step. Okay, so to really get a handle on the genius of Ezouidi's theorem, we need to meet the challenge head on. Picture this: a monstrous equation, 19 terms long. It starts with x to the power of 19, and it's filled with coefficients ranging from, well, small numbers like 19 or 171 up to massive seven-figure numbers later on. It's px equals minus 199 plus 1 and 2 minus 969 my. It just keeps going term after term, but these huge numbers, all the way down to positive and negative coefficients like minus 11 million x cubed plus 4 million x squared, no x term, and then minus 831,375 equals 0. You can see why finding an exact solution feels, well, daunting. This is the beast Ezouidi's theorem is going to tame today.
Yeah, it's quite the mouthful numerically. But conceptually, this polynomial can be expressed using general coefficients. Think of it like a template. Px for Susha plus no, and so on, right down to the constant term, which is for us false. For our specific problem, these L key values are precisely defined numbers. So L is 19, L1 key is 171, L2 key is 969. Point L key is 307 and 66, all polar keys 11638, all four keys also 700 132. It continues like that. All six keys 403 all seven keys 7 over 5582. Then LTs is actually just 1, then they become negative. All no keys 19 over 81,383. All upping keys all additional 83,582. All 10 keys all out of 90,991,383. All TTs and national 4,081,376. All 14s is nation in 1,134,871. All 60s entered 4,176,775.
Wow. So these aren't just random numbers. They are the precisely defined components of this specific challenge. It really underscores the complexity Ezouidi's theorem is designed to handle.
Exactly. And what's truly revolutionary about Ezouidi's theorem is how it solves this exactly. It uses a recursive process. Basically, it finds the precise values of the roots symbolically, step by step. This completely avoids any approximation errors that you'd get with numerical methods. The core mechanism involves re-expressing the polynomial. It uses a new set of symbolic coefficients, let's call them SK1Q, or just S coefficients for simplicity. These S coefficients are calculated recursively. Think of it like a recipe where each new S coefficient is built from the original polynomial's coefficients, those L values we just listed. The general formula, it looks complicated, but it basically involves combinations, binomial coefficients, terms related to the polynomial's degree, and that very first coefficient, L0Q, plays a key role. It's all calculated systematically.
Right, so the power here is that every single one of these newest coefficients is determined symbolically. It's not crunched into a decimal approximation at this stage. That's the key to avoiding those rounding errors, isn't it? Keeping it exact.
Precisely. It means we keep everything in its exact form, fractions, roots, powers, never converting to an approximate decimal until maybe the very final step if you need a number. This recursive process, because it stays purely symbolic, ensures perfect precision. And when we apply this process to our specific degree 19 polynomial, something really fascinating happens with these new S coefficients. Okay, so we calculate them one by one using that recursive rule, and a remarkable pattern just pops out. Most of them turn out to be 0. So 0R through S7R, all 0, gone.
Just 0. Wow.
Then we hit S8R. This one is significant. It's a non-zero value. Minus 92,377 times 19 raised to the power of 9. It's an exact symbolic value.
Yeah.
After that, the pattern resumes. S9Q right through to S16R, all 0 again.
More zeros. That's quite elegant.
It is. And then we get one more non-zero value, S17R. This one is positive. 923,751 times 19 raised to the power of 18. Another exact symbolic value. And finally, S18R, also 0.
That is pretty remarkable, the way so many complex calculations seem to just cancel out, leaving only 2 key non-zeros values. What does that tell us?
More than just convenient, yeah. It really points to an underlying, almost hidden structure within these seemingly intractable polynomials, a structure that Ezouidi's theorem is specifically designed to exploit. It suggests a potentially deeper, maybe more unified way to think about polynomial theory. And the immediate payoff is huge. Once these S coefficients are determined, they let us rewrite the original polynomial equation in a much simpler form. Remember the general form using S coefficients. It was RxO, Rxa plus S1 Rxe, and so on. But now, plug in all those zeros we just found, and our massive degree 19 beast transforms quite dramatically into this. Px is x sa7 plus s17 rx s s18 q rs a. Wait, let me recheck the indices based on the standard form. All right. The general form using these coefficients is actually PS S0 Rxa plus S1 Rxa down to plus S17 Rx18 Rx8. But wait, the constant term needs caret. Let me check the source derivation again. Okay. The source actually reformulates it slightly differently by the end. The key insight is that with 0 through S7 being 0 and S9 through S16 being 0, the polynomial simplifies massively. It becomes x8r x19 to 9 plus s17r x19 to 18 equals 0, assuming a specific relationship with the constant term, or rather, let's look at the version derived in the paper. The paper shows it simplifies directly to px as xxr xxu plus s17r equals 0. That structure makes more sense with the indices.
Okay, x times xo arrow x8r xers plus s17r equals 0. That simplification is, well, it's the core elegance of the theorem right there, isn't it? It immediately gives us one root, x saving, simplify that one down, and it reduces our massive problem to solving a much, much more manageable equation. x8r x8r xx plus s17r equals 0. That's a huge shortcut.
It really is. Now we just substitute the exact symbolic values we found for S8R and S17R into this simplified equation. So we get xy 192377 I17R x plus 193751 times 19 euro, or cleaning up the sign, XOR plus 92377 times XO plus 9233751 19 euro equals 0. Now look closely at this equation. Even though it has XO and XO, it structurally behaves just like a quadratic equation.
Ah, I see. It's quadratic in terms of XO. It's like XOR plus some coefficient of X plus another coefficient.
Exactly. Which means we can solve for XR using a variation of the good old quadratic formula. The formula gives us XXR, coefficient of XR, coefficient of XR, coefficient of XR, which is 1, constant term, 2, coefficient of XR. So XR, 92377 is minus sum and 41, 923,751 by 19.2. Let's call that term inside the square root the discriminant. It simplifies, believe it or not. The source material calls it 90test1r and calculates it as 852981512 19r.
Wow, still exact numbers, even inside the square root.
Still exact. So XR 92377 by 19r, 1990 square root 723 19r, 19r. We can pull the 19r out of the square root as 19r. So XR is 19377 minus square out 852981512. We have 2 exact symbolic values for XR.
Okay, so that gives us XR. But the original problem was degree 19. We need the values for X. How do we get those?
Right. For each of those 2 values of XOs, we now need to find the 9th roots. Finding the 9th roots involves complex numbers, specifically roots of unity. For any complex number z, its 9th roots are given by z19 ei, theta plus 2k9, where theta is the angle of z and k goes from 0 to 8. So combining everything, the final symbolic form for the 18 non-zero roots looks like this. X sub k is 19 times 92377s, my openness square t, 852981515, multiplied by e to ki9. Here, k runs from 0 up to 8, giving us 9 roots for the plus sign in the amena, and another 9 roots for the minus sign. That's 18 roots.
Plus the XO root we found earlier makes 19 roots total.
Got it. And that final expression, intricate as it looks, is the absolute key takeaway here. It's the core power of Ezouidi's theorem. These are exact symbolic roots, not approximations rounded to some decimal place. This theorem delivers precise, unambiguous solutions where classical methods just hit a wall or give estimates, completely free from rounding errors. That's the fundamental difference. This method, because it stays symbolic throughout the recursive calculation and the final root extraction, doesn't rely on numerical approximations at all. That's the game changer. It guarantees the roots we obtain are exact, free from those inherent errors. It provides a pathway to precision for these high-degree polynomials that were previously considered too complex for exact classical methods.
So we've really taken you on quite a journey here. We started with what seemed like an insurmountable challenge, this degree 19 polynomial, huge coefficients, lots of terms. And we walked through how Ezouidi's theorem systematically breaks it down and delivers precise, exact symbolic solutions. Pretty incredible.
And if you think about the bigger picture, this profound difference between getting an exact symbolic solution versus just an approximation, well, it opens up entirely new possibilities, not just in pure math, potentially. It's really about moving beyond close enough to actually achieving perfectly known. That's a fundamental shift in thinking for certain types of problems.
Right. So what does this all mean for you listening? Well, if a method like Ezouidi's theorem can unlock exact answers for problems we thought were unsolvable or only solvable approximately, then what other long-standing unsolvable problems out there, maybe in mathematics, maybe in physics, engineering, maybe even economics or biology, might just be waiting for a completely new way of looking at them, a different angle, a paradigm-shifting approach like this one? What insights might we be missing simply because we're sticking too closely to the traditional methods? Something to think about until our next deep dive.